In this video, we'll be going over power series for complex numbers, and we've seen that throughout this series we've been doing a lot of counterparts. For example, we did limits for complex numbers, just like there's limits for real numbers. We did functions for complex numbers, just like there's functions for real numbers. So here we're going to do power series for complex numbers, just like there are power series for real numbers. And the reason we're doing these over again after the real numbers case, why we're doing it for complex numbers, is that it's not necessarily always true. If something is true for real numbers, it's not necessarily always true for complex numbers. There is a majority of cases where they do agree with each other, but there are important cases where they don't. So it's important that we prove things over again in complex numbers and don't just take them for granted. So let's go ahead and start. We'll start with the definition of power series. So a power series is an infinite series of what form? So the form is like this. Sum, as n goes from 0 to infinity, of a sub n, which is the coefficient, z minus z naught to the power of n. So let's just label some things. So a sub n, as I mentioned, is the coefficients of this power series. And these are, important thing to note, these are complex numbers. So these can involve i's and anything. And then z naught is called the center of the power series. Okay, so now I want to go straight into a theorem. So this is going to be called theorem A, and we'll go over the proof, which I've written out after I write down the theorem A. So theorem A says that suppose there is a z1 not equal to z naught such that the sum of a sub n z1 minus z naught to the n converges. So that's a supposition. So suppose there is some z1 not equal to z naught such that this converges. And of course this is going to be n equals 0 to infinity. And now what the conclusion is that then for all z, so this upside down a is a for all z, with z minus z naught is less than z1 minus z naught, and this is the modulus. So the modulus of z minus z naught is less than the modulus of z1 minus z naught. The sum a sub n z minus z naught to the power of n converges. Not just converges, converges absolutely. So this seems kind of messy right now. Maybe we're not really sure what's going on, but in the proof it'll make more sense. So I've written it again on this proof paper. So let's just go through the outline of the proof. So let's look at the statement again. Suppose we're going to look at this picture and the statement at the same time, so we'll get a feeling for what's going on here. So suppose there is a z1 not equal to z naught such that the sum from 0 to infinity, and sometimes I just write 0 here, but really you should think of it as n equals 0, from 0 to infinity of a sub n times z1 minus z naught to the power of n converges. Okay, so what does that mean? So I've drawn a little picture here, which I've enlarged the circle. So here's z naught. Z naught, remember, is some point on the complex plane. Z1 is some other point on the complex plane. So if we take their difference and we raise it to the power of when n equals 0, and then next we go n equals 1, n equals 2, and then we multiply that by the coefficient each time, this will converge, okay? If that converges, then for all z in which the modulus of z minus z naught, so that means for all z in which the distance from that z to z naught is less than the distance from z1 to z naught, then that new series here concerning that new z is absolutely convergent. So what does that all mean? So here is, I've drawn the circle, and the size of the circle, the radius, is the distance from z1 to z naught, also known as modulus z1 minus z naught, right? Because modulus a distance. And everything, all the little purple lines in here, is representing the inside of the circle only, not the exterior, which is why it's dotted, inside the circle. Every point in that inside of the circle, every z in there, satisfies this condition, because the distance from any purple point to z naught is less than the distance from z1 to z naught. And we just see that geometrically. And then if we take that distance and then we put it through this series, that will be absolutely convergent. So now we kind of see why this might be true, because now we're taking a smaller distance and we're adding it over and over again. So it seems like that should be convergent because that's smaller than the sum here. So if this sum converges, that sum should converge. But nonetheless, we need to prove it. So let's go right into the proof. It's not that bad of a proof. So the proof starts here. Suppose that z minus z naught, the modulus, is less than or equal to r, and that r is less than the modulus z1 minus z naught. So to illustrate what that means, I've enlarged this picture and I've added some extra details. So again, here's the z naught, and on the orange circle on the outside, here's z1. Okay, and now I've drawn some z, any z that is inside this purple area. So I've drawn it here for the sake of simplicity. And now we have this new pink circle whose radius is some r. R doesn't concern us. We don't need to care about exactly what value it is. What we do need to care about is that r is bigger than the distance from z0 to z, but it's smaller than the distance from z0 to z1, which is why I've drawn an intermediate. And the important thing is we can always form a circle like that. And the reason for that is because this purple disk right here is an open set. So we can get infinitely close to z1. Z can get infinitely close to z1. But there will always be enough distance in between so that a circle of some radius can fall between them. So try to wrap that around your head. It just has to do with how this is an open disk, and when we have numbers, there's no such thing as two numbers that are next to each other. Like, there's no consecutive numbers because numbers have infinitely many gaps between them. Okay, so next step in our proof is to look at this statement. Since we know this is convergent, why do we know this is convergent? Because that was suppose it's convergent. So we know this is convergent. What do we know? That means the limit as n approaches infinity of this inside approaches 0. And why do we know that? Well, that has to go back. We go back to a single variable calculus and look at how if a series is convergent, then the terms have to go to 0, because if they don't go to 0, then the series can't be convergent, because we're just going to keep adding things that are bigger than 0 over and over again. So that means that this sum, the terms in the sum have to go to 0, and so that means this is true. So since this is convergent, the limit equals 0. And furthermore, there exists some constant m, okay, such that, and now we're going to use absolute values. We're going to have modulus a sub n times modulus z1 minus z0 to the power of n is less than or equal to m. So now you're thinking, what does this mean? Well, think of it this way. If you have a series like this, there's always going to be a biggest term in the series, right? So you can't have the biggest term be infinity because this is a finite series. So even though the biggest term is huge, it's still not infinity. And since that's the biggest term, all other terms are smaller than that. So if we say that that means there exists that constant m, and m will be that biggest term, such that the absolute value of the terms in the sequence are always less than that biggest term. And why we have to put absolute value is because for some sequences, let's say in real numbers, can have an alternating negative positives. So we can have like -5, 4, -3, 2, -1, and so on. So so if we take the absolute values of these, it's going to be 5, 4, 3, 2, 1, and the biggest value will be 5, assuming that these just keep getting smaller in absolute value, nothing weird happens down here. So the same thing with complex numbers. We will take the absolute value, and the absolute value will always have a maximum, and that maximum will be m. And this is true for all n, so all terms in the series, as we discussed. So now, we'll finish this proof off. So now I've written here, absolute value a sub n times modulus z minus z0 to the power of n equals this, and this seems kind of messy, but if you just look at this term right here, z1 minus z0 to the power of n, that's the same term as z1 minus z0 to the power of n right here. So these can technically cancel, and you'll just be left with a sub n times z minus z0 modulus to the power of n, which is exactly what we have right here. So I've just written this in expanded form. And this right here is always less than or equal to m times p to the power of n. I'll explain what p is in a second, but what is m? So we said that absolute value a sub n times z1 minus z0 to the power of n is always less than or equal to m. So remember, so we look at this, and this is the same thing as this whole term right here. So that is always less than or equal to m. Now what about this right here? So p is defined as r. Remember what r is? In fact, I've written it here. So r is that intermediate disk, and we've remember that z minus z0 modulus is less than or equal to r, which is what we have right here. So z minus z0 is always less than or equal to r. So that means that z minus z0 to the power of n is going to be less than r to the power of n, which is exactly what we see when we have p to the power of n, because that includes r to the power of n. So just to recap, we have modulus z minus z0 over modulus z1 minus z0, all to the power of n. And since r is greater than or equal to z minus z0 modulus, p to the power of n has to be greater than z minus z0 modulus over z1 minus z0 modulus. Okay, so this holds true. So that means that this right here is less than or equal to this. And now to finish this off, since this sum right here, so sum n equals 0 to infinity, m times p to the power of n converges. And why does that converge? Well, let's look at it. This sum right here, m is a constant, so we can factor it out. It doesn't really affect the convergence or divergence of this series. So what about p to the power of n? So, well, we have this p, and this p is a fixed number, right? Because r is a fixed number, z1 minus z0 is a fixed number. And furthermore, we know that z1 minus z0 modulus is greater than r, which makes p less than 1, which means that this is a geometric series. So go back to your algebra or geometry calculus to remember what geometric series is, but the fact that this is a geometric series right here means that it will converge, because the absolute value of p, this ratio factor, is always less than 1, which is what we said here. Okay, so now the final statement that we have to say is that since we establish here that each this is always less than or equal to this, that means each term in this series, so each term in this series right here, is less than its corresponding term in this series. And since this series converges and each of the terms in this series is less than this one, this also converges. And that means that our series right here that we were trying to prove is absolutely convergent. Remember what absolutely convergent means? It means that if we take the absolute value of this series, which we did here, that converges. And since this converges, that means that this converges. Because if a series is absolutely convergent, it is convergent. So I know that was a big mouthful. If you want to understand this proof thoroughly, go through these steps again. It is important to understand it thoroughly for the sake of future proofs and things like that. But the basic idea, let me just go through it super fast, is that we established an intermediate R, and the reason we did that is because we want to use it for a geometric series test later. We established that the limit has to go to 0, and also that there's a maximum number. And these are all ideas from calculus. And then we said that we said that this series is less than this series, which is like a comparison test. We said that this is less than this, so we compared these two series, and we said that this one converges, therefore this one converges. And since this one converges, it is absolutely convergent, which means the original series without the absolute values is also convergent. So all of that to prove that this is absolutely convergent. So now let's get back to the new information in this video. So we've gone over theorem A, we proved it true. The next topic to talk about is called radius of convergence. So you might have remembered this from calculus, the series part of calculus, but we'll go over it again. So radius convergence, there are 3 different cases. Case 1 is that this series, sum from 0 to infinity, a sub n, z minus z naught to the power of n, converges only when what? Well, only when z equals z naught, in which case the radius of convergence, which we'll label r, is going to be 0. Okay, and that's because if we draw a little graph and we have our z naught, we can't go anywhere because no other points work. So we just have the point z naught, and the radius of a point is kind of, you can say it's 0. The next case is the same sum right here converges for all z, and that is the extreme case, the opposite case of this. So that would be if you have z naught, you can have any point in the complex plane you want, it'll converge for that. And then we kind of say here the radius convergence is infinity, because you have an infinitely big radius because it's the whole plane. Okay, and the last case, which is the one that'll be of interest to us mostly, is that the same series converges for only some z that are not equal to z naught. So the important thing is that there's at least one z separate from z naught for which this converges. So you can put at least one z different from z naught in here such that this has a converging value. Okay, and in that case, we say the radius of convergence will be some positive number. For example, this is just an example, radius of convergence equals 5. That means that the distance from z naught is 5. So everything within a 5 unit radius of z naught will be convergent inside that disk. So we'll see more of that right here. So now we're going to analyze case 3 a little bit further. So what does radius of convergence r actually imply? So I've written what it implies here. So that means if this modulus z minus z naught is less than r, so let me draw a picture because pictures usually help. So here's our z naught, and let's say this is our r. So this is the distance r. And so if we choose everything inside the circle, not on the boundary, so I should have drawn the boundary open disk, but not in the boundary, so everything inside here, these dashed lines, then this series right here will what? It will converge. But if we choose something outside the boundary, so if we choose anything out here, if we choose anything outside the disk, then this series will do what? It will diverge. There will be no value that it is limiting to or converging upon. Now, there is a third case, of course. So what if we have it equals r? So what if we choose any point on the circle's boundary? Well, that's the ambiguous case. We do not know. It could converge, it could diverge. We have to use some different methods to figure out which one it is. So remember, less than the radius convergence converges, greater than radius convergence diverges, equal to radius convergence ambiguous. We don't know. So now we're going to go over two familiar tests, the ratio test and the root test. Root test is probably less famous, but the ratio test, probably you've heard of it. So let's go over the ratio test. So we're just going to do these via example. So we want to find out whether this sum right here converges. And we want to find out, furthermore, what is the radius of convergence. So the ratio test says that you take the limit as n approaches infinity of absolute value or modulus of the term n plus 1 over the term n. So we're going to do exactly that. We're going to do limit n approaches infinity. So what is term n plus 1? That involves just putting n plus 1 everywhere I see an n. So it's going to be negative 1 to the n plus 1 z to the n plus 1 over n plus 1 factorial. And now I'm going to multiply by the reciprocal. So I'm going to multiply by the reciprocal of the nth term. So that's going to be n factorial over z power of n, negative 1 to the n. Now, important to note, since this is an absolute value or modulus, everywhere you see a negative 1 to the power of n, negative 1 to the power of n plus 1, that just cancels out because it's just going to be a positive or absolute value number. So next thing to do is rewrite this a little bit. So we have z to the power of n plus 1 can be broken up as z to the n times z. And now we have n factorial over n plus 1 factorial can be written as n plus 1 times n factorial, and we have z to the power of n. So lots of canceling going on here, and we're left with z over n plus 1, and the limit as n approaches infinity. So as n approaches infinity, the denominator gets infinitely big, and z over something infinitely big will be 0, because z is going to be some complex number. And the absolute value or modulus of 0 will be 0. So this is going to be 0. And now, what does the ratio test say? The ratio test says that once we do this, if we get something less than 1, then it's convergent. If we get something greater than 1, then it's divergent. If we get equal to 1, questionable. We don't know. We have to use some other test. But in this case, we got 0, which is less than 1, so this is convergent. And furthermore, what is the radius of convergence? It's going to be infinity. And why will it be infinity? That's because 0 is always less than 1. There is no condition. So we'll see, if you do the ratio test on some other examples, you might get some function of z. For example, let's say you got z minus 1 has to be less than 1. That means, or absolute value. So that means that centered at 1, the disk centered at 1 with radius 1, everything inside there will be convergent. But in this case, since 0 is always less than 1, it's going to be infinite, because we can put any z we possibly want, and 0 will still be less than 1, as it always is, and it'll be convergent. So convergent radius of convergence is infinity. Now the root test is a little bit less known, and you'll probably be using it less, but it's nonetheless important. We can go over it really quickly. So root test says that you take the limit as n approaches infinity of the nth root of, and we do absolute value or modulus again, the nth term. Okay, so let's try to do it for this example in the space we have right here. So we're going to have limit as n approaches infinity, and instead of putting nth root, I'm going to put to the power of 1 over n to make this a little bit faster. So we're going to have, so t sub n will be 5 to the power of n, z minus 1 to the power of n, to the power of 1 nth. And now since 5 to the power of n is positive no matter what, we can take it out of this absolute value altogether. And then we have 5 to the power of n times to the power of 1 to the power of n. So this n and 1 over n cancel out to make simply 5. And then we have z minus 1. And that's going to be, I'm going to shift these absolute value of modulus inside of it. And the same thing will happen, n and 1 to the power of n. So it's going to be to the power of 1. And we'll leave it like this. And that has to be less than 1. So the conditions of the root test are the same as ratio test. If this limit is less than 1, convergent, greater than 1, divergent, equal to 1, ambiguous. So we have to have it less than 1. Now we see here, here's the case where the limit involves z. So this is going to be z minus 1 is less than 1/5. So the radius convergence in this case will be 1/5 because we have this the z centered at 1. So if we draw a little tiny picture centered at 1, and how big can the circle be? It can be 1/5. That's the radius. So the radius convergence is 1/5. So again, ratio test, more important, root test. It is useful in some cases, but we could have just easily used the ratio test here actually. So not too big of a deal. So now we're going to go into the main new topic of this video, which is the derivative of a power series. So I've written the gist of what the information is in green here. So it says that if f of z equals the sum from 0 to infinity of a sub n times z minus z naught to the power of n, and let's just take this moment to talk about how this is written. So since this power series it's really just a function of z, correct? Because this a sub n, these coefficients are fixed. And this z naught is fixed. All you're really changing here is z, because this is an infinite function. It goes on forever, but it's still a function. You can plug in z, and so it can be a function of z. So it is f of z equals this series. If this series or function has a positive or infinite radius of convergence, okay, so not 0, then inside this disk, modulus z minus z naught minus r, so disk centered at z naught with radius r, inside that disk, f of z is what? It is infinitely differentiable. And what does infinitely differentiable mean? It simply means that you can take the derivative once, you can take it twice, you can take it 3 times, you can take it 4 times, you can take it infinitely many times, and you won't encounter any problems whatsoever. It'll just keep being able to differentiate. Eventually, maybe you might get to a point where the function, some derivative is just 0. Well, that's not a problem. You can differentiate 0, you just get 0, and just keep doing that over and over again, no problems. So basically it means you run into no snags, no division by 0 errors, nothing like that. And furthermore, each derivative is given by another power series. So if you take the derivative of a power series with an infinite or positive radius of convergence, you get another power series. And then you take the derivative of that, get a new power series. And what is each derivative given by? So this notation right here is the kth derivative of f evaluated at z. So it'll be, for example, if k was 1, it'll be the first derivative of f, and you put in whatever z you want. So that is given by this new sum. So the sum from should be at n equals k. So the sum from n equals k to infinity of n times n minus 1 all the way up to n minus k plus 1 times a sub n times z minus z naught to the power of n minus k. So you're probably thinking right now that's very messy. So I agree, it's very messy. So we'll just do it. We'll look at it by example and not worry too much about the exact definition. So let's just go right into this example. So let me remind you again, of course, I put the 0 here. It should be at n equals k. So you're starting at k. You're not always starting at 0. Okay. Okay. So our example is here. We have f of z equals the sum from n equals 0 to infinity of n times z to the power of n. So I've written a few terms out here. So the first term would be 0 times z to the power of 0, so it would be 0. Next term would be 1 times z to the power of 1, so it's z. Then it's 2z squared, 3z cubed, and so on. So the exponent and the coefficient, basically they match. So what is the first derivative? And we're not going to do it using this complicated formula. We're just going to do it using inspection, right? So we'll do it term by term. What's the derivative of 0 with respect to z? Well, it's 0. What's the derivative of z? It's going to be 1. What's the derivative of 2z squared? It's going to be 4z. What's the derivative of 3z cubed? So it's going to be 9z squared, and so on. Now, does that match? What we want to see is, does that match our definition right here? If it matches, then we see this definition is it's true. Okay, so let's put this through the definition. So we want the first derivative, right? So in this case, we want k to be 1. So we're going to have k equals 1. And so n equals k is going to be n equals k equals 1. And then we're going to have n minus k is really n minus 1. And we're going to have n minus k plus 1 is really n minus 1 plus 1. So it's just n. So that means that all we're really dealing with is this n, none of these other terms. So if we rewrite this, it's going to be sum from n equals 1 to infinity of n times a sub n z minus z naught to the power of n minus 1. Okay, that should be the derivative. So that should, once we expand it out, give us the same answer as 0 plus 1 plus 4z plus 9z squared and so on. So now, what is z naught in this case? Z naught is 0, because there's it's really z minus 0 right here. So this is nothing, this is 0. What is a sub n? A sub n was n, so this is going to be n. So we'll just finish this up on a new paper, and So this is the series we're left with. After everything cancels out, we have 2n, so we have n squared, and then we have z to the power of n minus 1. And now we're going to put in 1 in here. What do we get? We get z, 1 minus 1, z to the power of 1 minus 1 is z to the power of 0, so it's going to be 1. And when we put in here, we get 1. So we get 1 plus. Now when we put in n equals 2, we get 2 squared is 4. Z to the power of 2 minus 1 is z to the power of 1, so it's just z. Now we put in z equals, when we put in z equals 3, we get 3 squared is 9, and then we have z squared. So we see that it's matching up exactly with what we did using just observation, using just term-by-term derivatives. So the last instruction here we'll be doing is that we'll be seeing what happens if we plug in z equals z naught into this thing. So I've written out the formula for the kth derivative again, and we're going to see what happens if we want the kth derivative of z naught. And remember, z naught is the center of the series. So we're going to have, let's see how this formula transforms. We have n equals k, infinity, n minus 1, goes all the way down, a sub n. But now here's the big difference. Since we have z minus z naught, and z is z naught, this is going to be 0. So we're going to have 0 to the power of n minus k. So you're probably thinking this is going to have to be 0, right? Because there's this big fat 0 here, multiplied by anything. Well, there is a slight nuance, and let's find out right now. So let's go ahead and just start writing down the terms of the series. Since we start at n equals k, let's plug in k. So if we plug in k here, we get n times n minus 1 all the way to, if n is k, then it's k minus k, which is 0 plus 1. So this is really just k factorial. So it's going to be k times k minus 1 all the way up to 1. So it's going to be equal to k factorial times 0 to the power of what? So since n is k, k minus k is going to be 0. So it's going to be 0 to the power of 0 plus, and then what's the next term? It's going to be k plus 1. So we're going to have k plus 1 and then k plus 1 minus 1, which is just k. So it's going to be k plus 1 times k plus, all the way up to, and these are all times, k plus 1 minus k plus 1, which is just 2. And then it's going to be 0 to the power of k plus 1 minus k, which is 1. And 0 to the power of 1 is definitely 0. So it doesn't even matter what all this is going to be 0. And for that matter, any further terms are just going to be 0, because the next term will have 0 to the power of 2, 0 to the power of 3, and they're all going to be 0. But let's look at this first term really fast. What is 0 to the power of 0? If you use L'Hopital's rule, so if you evaluate this limit as n approaches 0 of n to the power of n, so that's going to go to 0 to the power of 0. If you evaluate this using L'Hopital's rule, you're going to find that this is actually 1. So that means that this is actually k factorial, and I think I left something out. So this should have a to the power of k here. So it should be multiplied by a to the power of k. And this should have been multiplied by a to the power of k plus 1, but that canceled anyway. So it's going to be k factorial times a to the power of k. So in the end, what do we have? We have the kth derivative at z naught equals a to the power of a sub k times k factorial. And let's write this in a form that we're going to see in future videos. So I'll write it up here. The form that we're going to see in future videos is a sub k equals f kth derivative evaluated at z naught all over k factorial. So this thing you see in black up here, it's very important. We're going to use later on for different series and evaluating new kinds of things. So again, it's a sub k. So the kth coefficient in this series is given by the kth derivative evaluated at z naught divided by k factorial. Okay, so keep that in mind. The last thing we'll be doing is a involved example, which kind of puts together everything we've learned in this video. So here we have a series. We have sum from n equals 0 to infinity of z to the power of n minus n factorial, and we know this is convergent with radius of convergence infinity, because if you go back to the part of the video that was about ratio test, this is the series we did, except it had a negative 1 to the power of n in front of it, but that went away anyway. So they're both convergent with radius of convergence infinity. And here for emphasis, I've written that the coefficient a sub n is given by 1 over n factorial. So that's what this is. And z naught, the center of the series, is going to be 0, because we see that it's just z to the power of n. So it's really z minus 0 to the power of n. Okay, so now what do we want to do with this? We would like to find the derivative of this. So let's use the formula right here that we have. We want to find the first derivative only. So we're going to go ahead and write f, I'll put a 1 here instead of prime, just to emphasize that it's the first derivative, f prime of z. Well, it's going to be what? It's going to be, first I put a sum, and then n equals k, and n equals 1 in this case, to infinity, times n times all of this stuff. But really, if we remember the first derivative problem we just did, it's just going to be n. And then what do we have? We have a sub n, so that I've written here is 1 over n factorial, so 1 over n factorial, times z minus z naught is 0, so just z to the power of n minus k. So it's z to the power of n minus k, which is 1. So now we have, this is going to be, and this n over n factorial will do what? Well, we have n over n factorial, which is n over n times n minus 1 factorial. So that'll cancel, and we'll be left with 1 over n minus 1 factorial. So this, all after this dust clears, is sum n equals 1 to infinity of 1 over n minus 1 factorial z to the power of n minus 1. And since we're starting this series at 1, but let's just start it at 0 so that we can take this n minus 1, and put an n instead. So n equals 0, infinity, z to the power of n over n factorial. So convince yourself that this right here and this right here are equal. I just started this one at 1, I started this one at 0, but if you write out the terms, they're the same exact series. And furthermore, here's the very, very interesting thing to know. This right here, sum from 0 to infinity, z to the power of n over n factorial, is the exact same thing we started with, which means that f, if we called this f of z, then this equals f prime. F equals f prime. It is its own derivative. And what function do we know that is its own derivative in calculus and things like that? Well, it's the exponential function. So let's do, as the last part of the video, let's really fast prove that f is the exponential function, that the exponential function is given by this power series by doing this. So what we're going to do is we're going to look at the function e to the negative z times f of z. And we're going to take its derivative. So we'll do a power series really fast. So it's going to be this times the derivative of this times the derivative of that. So it's going to be minus e to the negative z, f of z. And since f prime of z is equal to f of z, we could just put a prime right here. So what we have is e to the negative z times f prime minus e to the power of negative z times f prime. So this is just 0. And what does that mean? That means the derivative of this is 0. And what kind of things have derivatives of 0? Constants, which means that this function inside here is a constant. So e to the minus z times f of z is equal to some constant k. And the last thing we want to do is try to figure out that constant. So we're going to write down e to the power of negative z times f of z equals that constant. We write that. And so it doesn't matter what number we plug in here for z, it's going to be a constant. So let's plug in 0. So we get e to the power of negative 0 times f of 0 equals k. And e to the power of 0 is 1 times f of 0 equals k. What is f of 0? Well, let's write down what f was again. F of z we said was this sum. We said it was sum 0 to infinity z to the power of n over n factorial, right? So if you plug in 0 in here, then the 0 becomes a 0, and we start with 0 to the power of 0, which is 1, we said using L'Hopital's rule, and so it equals 1. And now if we put n is bigger than 0, so if n is 1, 2, 3, 4, all these other terms are going to be 0, so that means f of 0 is 1. So we have 1 times 1 equals k, so k is itself 1. So that means that e to the minus z times f of z equals 1. So that's using this step right here and plugging in what k is, what we found k to be. So now if we just move this e to the negative z to the other side, we get f of z equals e to the power of z, and we're done. We've proved that this infinite series right here represents e to the power of z. So remember, we did that for real numbers, but as I noted at the beginning of the video, we can't always assume things for complex numbers that are true for real numbers. But now we have proved that this case in particular is true. F of z does equal e to the z. So in the next video, we'll be going over a new topic, Cauchy's theorem.